Okay, in this video we're going to be having a look at anti-differentiation of polynomials. I'm actually going to start with some differentiation. Okay, so we want to find f dash of x when f of x equals x squared. So remember our 2 comes down the front, so we get f dash of x equals 2x. Okay. Similarly, if we look at f of x equals x squared plus 4, well we know our 4 drops out, so we're going to get f dash of x equaling 2x also. Okay, and we can see that if we, for all these examples, f dash of x equals 2x. Okay, and I want to highlight the fact that this is the case because the idea around anti-differentiation is that we start with a derivative function and we go back to an original function. But the problem we've got here, okay, so we can see that all of these have the same value. Okay, so all of these functions go to the same derivative. So if we're trying to find our antiderivative, we're going back the other way. We don't know whether there's going to be a number here or not. Okay, and we need a way that we're going to handle that. Okay, so that brings us to some of our first ideas around anti-differentiation. Okay, so we can demonstrate this idea from a graph. Okay, so we know our derivative is always f of x equals 2x. Okay, so if we're trying to find a graph, an original function, we know that it has to be a quadratic because we're a linear function for a start, which is fine. Okay, and we know that the turning point has to be at 0 because 2x goes through the origin as well. Sorry, our turning point has to be at the has to line up with our origin. Okay, but it can be up here, can be down here, it can be down here. Okay, so the idea here is when we find an antiderivative, okay, we need to be able to represent this constant value at the end that we don't know. Okay, so in order to be able to do that, okay, we need to get some notation down. Okay, so if we use capital F of x and we say f dash of x, so if our derivative of capital F of x equals little f of x, okay, then if we find our antiderivative, now this is a new notation here, and I'll explain this. Okay, so we're saying that we had the derivative of a function equaling this other function. Now if we take the antiderivative, now this sign here is what we call an integral. And it means that we're finding our antiderivative of here. Now notice we've got a dx here, okay, similar with our dy dx notation for our derivatives, okay, because this was really our derivative of y with respect to x. Well, this is our antiderivative of fx with respect to x. That's what the dx means. Right? And we can say that's equal to capital F of x, again, because we know there's a link here, okay, plus c. And we need the plus c for this reason over here. Okay, c is just a constant, it's any number. Okay, it could be any number. Without other information, we can't actually work out what that c value is. If we were given a little bit more information, we could. Okay, but at this stage we can't. Okay, and that's just to represent, well, it could be 0, like this case, or it could be anything else like this. Okay, so we've got to make sure that we have the c. So that's just a constant. Okay, so just to run through that again, this sign is called the integral sign, but we read this thing as we're finding an antiderivative of f of x with respect to x, and that's going to equal capital F of x plus c, where c is a constant. Okay, so we have some rules. Funnily enough, we have some rules. Now this is okay because we're actually seeing this, because if we think about this, we had x squared, okay, and if we found our derivative, it became 2x. Well, we need a process, okay, to actually go back this way, okay, and that's really stated here. Okay, so this is the rule that we just saw. Okay, now this one we talk about specifically our polynomials. So we've got x to the power of some number n. Okay, well here in this case, n is 1. Okay, so we want to go back this way. So we can see we need to add a power back to our original power. So our original power was n, we need to add 1 to it. So we say it's x to the power of n. Okay, but we don't have this 2 here anymore, that's gone. And we can get rid of that, okay, by dividing by the new power. Okay, so if we're reversing a process, okay, what we do is we increase our power by 1 and divide by our new power. Okay, so if I had x cubed, okay, that's going to become x to the 4 divided by 4. Okay, x squared is going to be x cubed on 3. Okay, and you'll see some other worked examples coming up too. Notice things that we've remembered, dx and plus c. So again, main ideas are increase the power by 1, divide by the new power. Now, if we have two parts to it, our equation, so we're finding the antiderivative of f of x, and this could be plus or minus g of x dx, so we're still doing with respect to x, you're allowed to split it up. Okay, so you're allowed to take something, split it into parts. So if we're looking at x squared plus 3x dx, I'm allowed to think of that as x squared dx plus the integral or the antiderivative of 3x dx. Okay, so I'm allowed to take this thing, I'm allowed to split it into parts and just do each part separately. Okay, for this one, we're saying that we've got some constant. Okay, so we've got some value here, k, right, and we're trying to find the antiderivative of k times f of x dx. What you simply do is bring the k out the front. Okay, now this might seem a little bit weird or odd, but essentially it's the way we handle the fact that we've got 3x squared. Okay, so if we were trying to find out any derivative of 3x squared dx, okay, we can bring the 3 out the front. And then we've got simply 3 times the antiderivative of x squared dx, and we'd be saying that that is 3 times x cubed on 3. Okay, and then our 3's are going to cancel out. Okay, and multiply through. Or if this was, say, 3 already, okay, then we're going to have 3 times x to the 4 on 4, okay, which is going to equal 3x to the 4 on 4. Okay, so essentially all we're doing is we can ignore the constant if you like, it doesn't actually impact on anything, but we could cancel down when we divide by that new power. So we'll have a look at a few examples I've got here to finish off. Okay, so we're asked to find the antiderivative of x cubed with respect to x. Okay, so remember we take our rule, we say, okay, well that's going to equal x raised to the power by 1, so 4 divided by that new power, which is 4. Simple as that, plus c. Okay, got to remember that plus c at the end, okay, because it could be a constant, there may not be. Okay, this one, okay, we've got lots of more components in this, doesn't matter, we do them separately. Okay, so you don't need to actually write it out as the integral of x squared dx plus the integral of 2x dx plus the integral of 3 dx. Okay, you can't just do it all in one go. Okay, so there's no need for that extra step. Okay, so we're going to say we're raising our power divided by our new power. Okay, raise our power by 1, divide by our new power. Raise our power by 1, okay, divide by our new power. If you like, that's 1, that's not going to change anything, plus c. Okay, so constant terms will actually now get an x. Okay, and we can simplify that slightly because our 2's are going to cancel out, so we'll be left with x squared, and we can just write it as 3x plus c, so that constant term. Okay, and see if we were to go back the other way, okay, and actually find our derivative of that, we would have been bringing our 3 down, it would have cancelled out, reduced our power by 1, gets us back to x squared. Okay, and we can keep doing that, and we're going to see that we'd actually get back to what we had, because this c would drop off, so we'd end up with the same thing. Okay, if I'm looking at this one, okay, again, okay, similar to here, but we've got this constant now. Okay, so I'm simply going to go 4 times x cubed, okay, because I'm raising my power by 1 and dividing by that new power, plus c. Okay, got to remember the plus c. Going something like this, okay, so something like this might initially throw you, okay, but you need to think, okay, I might split this one into parts a little bit and just think about this part for a second. The rest of it isn't going to cause us any dramas, but this part might. Okay, I can think of divided by 2 as the same as timesing by a half. So I've simply split it into two parts. I've taken the half out the front. Now you don't necessarily have to do it this way. I just want to really illustrate a point here. So we've got our half now, and I'm going to raise my 3 to a 4 and divide by 4. Okay. Now I'm going to be taking away each part here. Oh, now I need to be careful there because this is, we've got to make sure that we get our signs right here. So we've just got to take away each part basically. So, oops, and that was only x squared. Okay, so I'm going to increase my power. Okay, divide by my new power. Increase my power. Divide by my new power. And increase my power. Okay, plus c. Okay, so simply we can see here now when we had a fraction as our coefficient, well, we're just going to multiply our denominators. Okay, so this means that we're going to get x to the 4 on 8, take x cubed on 3. We can cancel out our 2, so we get negative x squared plus 4x plus c. Okay, so if we've got a fraction as our coefficient, you can think about bringing it out separately if you like to make it easier to do this multiplication afterwards. Okay, because in reality this could have been, say, 3 on 2. Okay, and we would have had 3 on 2 out the front, 3 on 2 there, and we would have simply had 3 on 8 times x to the 4. Okay, so again, a nice little rule here. Okay, so opposite to what we were doing. Okay, there's a lot of applications. We had antiderivatives as well, which we'll see in some later sections.